All right, well, we've talked about vector spaces and we've introduced vector space properties. But so far, whenever you think of a vector, you think of C3 or C2 or a certain number of components on a vector. So in this video, I want to introduce some other types of vectors so you can see that this concept is more general than that. Okay? Turns out that set of polynomials Pn with complex, let's start with complex valued coefficients whose degree is less than or equal to n forms a complex vector space. Now, you can have complex vector spaces where the scalars are complex, and you can have real vector spaces where the coefficients are real. So that's why I put the real in parentheses there. It's true that Pn of x with complex coefficients is a complex vector space. Pn of x with real coefficients is a real vector space. So let's think of what this means. For instance, if I wanted to do an example of P2, P2 of x is the set of all polynomials whose degree is less than or equal to 2. So it's equal to the set of polynomials whose degree is less than or equal to 2. So that would be polynomials of the form ax squared plus bx plus c. Sorry, that's a plus there. Where a, b, and c are complex. So you can think of any complex numbers a, b, and c, multiply a times x squared plus b times x plus c, and that's going to be an element of P2. Okay. All right, so here's an exercise. Give a counterexample that shows that polynomials of degree equal to n do not form a vector space. So it turns out that polynomials of degree equal to 3, for instance, do not form a vector space because they don't satisfy additive closure. For example, like I said, if you want to show something's not a vector space, you should find an example. Here's P1 of x, I can call x cubed. Now that certainly has degree 3. And P2 of x is minus 1 times x cubed. That also has degree 3. When I sum those to give, that's the zero polynomial, which doesn't have degree 3. So I take two degree 3 polynomials, I add them together, their sum does not have degree 3. However, the sum has degree less than or equal to 3. So that's not a counterexample to Pn. The polynomials of degree less than or equal to 3 are still a vector space. So that's something that's true. So this is one common example of type of vector space that's important in mathematics. Next one, we can take the set of n by m matrices with complex entries will be a complex vector space. And if we take n by m matrices with real entries, that will be a real vector space. Okay. Now the matrices don't have to be square, but they have to be the same size. And each different size of matrices gives a different vector space. So example, I could take M23, that's a vector space. I could take M57, I could take M1219. These are all vector spaces. Because you can add matrices of this form, or you can multiply matrices of this size by a scalar. Of course, you can't add a matrix here and a matrix here, so those are different vector spaces. Now, you should think about M23. It's really like 6 components. You could arrange those components in a column. That's very much like C6. It's just that you're arranging the numbers in a table with 2 rows and 3 columns rather than in a single column. So that's kind of how you should think about M23. It's just a rearranged version of C6. But it is still true that the rearranging doesn't change the vector space properties. Right? So that's another vector space. Now here's a vector space that's quite different. Let S be the set of all solutions of the differential equation d squared y dx squared equals minus y on minus infinity to infinity. Now if you have differential equations, you know that this is a homogeneous differential equation. We can bring the y to the other side. Turns out that this is a vector space. Now, I'm not going to emphasize this because I'm not sure that everybody's had differential equations, but just to show you that vector spaces are more general than what we've looked at before. Then we could also take the set of all continuous functions on the interval that are real valued. Then V is also a real vector space because sums and scalar multiples of continuous functions are continuous. So again, I'm not going to emphasize that in this class, and you see this kind of thing in real analysis. But you should be aware that this kind of vector space is out there. Vector spaces are not just component vectors, but they're also many other things are vector spaces also. All right, so let's go on to some exercises. All right, so this was one of the exercises that was mentioned in the outline. Suppose that V is a vector space and U, V, W are in V. If W plus V equals W plus U equals W plus V, then U equals V. This is called the law of cancellation. All right. So how would you prove this rigorously? Now, you need to justify every single step. Now, how would you cancel in usual arithmetic? If you just had this statement in usual arithmetic, you just subtract W from both sides. But we have to justify that in vector spaces. Do we have something that we add to both sides that we can cancel? And the answer is yes. If you go back here, you'll find that any vector has an additive inverse that we call negative, right? So if we have a vector U, we have a vector minus U that cancels it. If we have a vector W, we have a vector minus W that cancels it. So we should be able to cancel the W on both sides by adding minus W to both sides. So first of all, you need to cite that property. The additive inverse property here mentions that there's a vector minus U and V such that U minus plus minus U equals 0. So in particular, that means that there's a vector here such that W plus minus W equals 0. So I mentioned that's the additive inverse property. All right. So given W plus U equals W plus V, I can add minus W on the left on both sides. Whenever you have two things equal, you can always do the same thing to both because you're basically substituting one expression for the other expression. Okay? So I can add minus W to the left on both sides. So that would give me minus W plus U equals minus W plus V. Because I started with W plus U equals W plus V. I added minus W to both sides. Okay. All right, now what can I do? Can I cancel right away? The answer is no. I need to rearrange before I can cancel. I want to get the minus W and the W together. So I need to reassociate. I need to put the minus W and W together. So that's what I've done here. Instead of taking W plus U and adding minus W on the left, I can add these two first and then add U. So this is the associative property, just regrouping my addition. Right? Now, so you see here that the minus W is on the wrong side. Here we had W plus minus W equals 0. That's the property. That's what we have to use. So we have to bring the minus W to the other side in order to use the property. So that's what I did here. That's what I did here. I used the commutative property of addition, which says I can add the two vectors in either order and get the same result. Right, now I can use the property that W plus minus W is equal to 0. I'm using this property. So this is 0. And in fact, this is the 0 vector. So I probably should put that in boldface, but I think you can understand that this is the 0 vector. So 0 vector plus U equals 0 vector plus V. Now what you'd like to do is just say that's U equal to V, but you have to use the property here. When we talk about 0 vector, we have U plus 0 equals U. It doesn't say here that 0 plus U equals U. You have to use the commutative property to get the 0 to the other side. So by commutative property, U plus 0 equals 0 plus U equals U plus 0, and U plus V equals V plus 0. Now we can cancel the 0 here and the 0 here, and we get U equals V. So this is a rigorous proof with all the steps written out that W plus U equals W plus V implies U equals V. So typically we don't go through all these steps because associative, commutative, additive, inverse, these are very common properties, but at the beginning you really do need to see how all the steps work. All right. One more exercise that I leave to you, and you can find the answer in the book Solutions. This one is similar law of cancellation, and here you say that, so here it says, suppose V is a vector space, U and V are in V, and alpha is a non-zero scalar from the complex numbers. If alpha times U equals alpha times V, then U equals V. So you're basically canceling off the scalar. So you may use the fact that any non-zero complex scalar alpha has an inverse alpha inverse that satisfies alpha inverse equals alpha equals 1. So this is just like the real numbers. You can always find the inverse of a real number. Turns out you can always find the inverse of I should have said non-zero real number. You can always find the inverse of a non-zero complex number. All right. So you will have, in order to prove this, you will need to use multiplicative associativity and the identity property. So you can try this, and as I said, the answer is in the answer key to the book. All right.